So now that we've found this relationship, so we've applied our two boundary conditions, we know the relationships here, we can say, okay, let's plug in what we know K is. So K is equal to, if we go back above, K is right here, this 2me square root over, or 2 pi times 2me square root over h. So we can go ahead and write that down. 2 pi times 2me square root over h. And that times a is going to be equal to n times pi. Now to get rid of the square root, we can just go ahead and square everything. And we have a way to relate the energy to everything else that we have in this equation. So we have 4 pi squared times 2me over h squared times a squared is equal to n squared times pi squared. Now let's go ahead and solve that for the energies. And so this is what we want. This is what we're interested in. What are the possible energies? And remember, what we're going to find is that it's going to be quantized. It's not going to be any possible energy that this particle in the box can take, but only specific values of energy. And that's showing up because, again, we have our integers here, this n squared. So if we rearrange this, we get E, which depends on n, is equal to h squared times n squared divided by 8ma squared. So, because we're going to see a bunch of things cancel out, right? Our pi squareds are going to cancel out specifically. So these are the possible energies of a particle in a box. And that energy is quantized. It can only come in specific increments. And so we have the energies, and we can also say, we know what the wave function is. These are the eigenvalues, and the eigenfunctions are psi of x is equal to b sine kx. But we can say that k here is the same as n pi over a. If we take that equation that we had earlier, where we had to relate k times a equals n times pi. So we can say that our wave functions are b times sine n pi x over a. And so we've almost completely finished this problem. And we have what's called, our n here is what's called a quantum number. And you're familiar with quantum numbers previously from looking at hydrogen atom and orbitals and things like that. And so n is the quantum number that describes our different possible, what we call energy levels of our particle in a box system. So we can have n equals 1, 2, 3, 4, 5, 6, up to, in theory, infinity. And each of those, so each wave function will have a different value of n, and that'll have a corresponding energy that goes with it. And so we'll look at these wave functions a little bit, but there's one last thing that we haven't defined about this system, and that is this constant b that is in front of our sine, our wave function here. And so in the next video, we'll look at the idea of normalization. How do we find the value of that constant? And it's going to relate back to the probabilities distribution that we talked about previously.